zero air void curve is the ZAV curve. And this is a theoretical curve that represents the fully saturated condition. So we are finding the dry density and the water content relation when the degree of saturation is 100%. And it's a theoretical curve because it cannot achieve by compaction. And so you can just only calculate it. Right? And here, where is it? It's like getting rho d and W relation when degree of saturation is 1. And we know the dry density, and also dry density is defined as the solid density over 1 plus E void ratio. And we know this relation at least, SE equals W times GS. So from there, here we don't know the void ratio, so we can replace it with the known value here. So then you get this equation. Very simple. So rho d is GS times water density times S over S plus W times GS. Here if you calculate the ZAV, you can assume the S is 1, right? So this will be 1 and this will be 1. So rho W GS over 1 plus W GS. Rho d. Right? We know the water density is 1 gram per cubic centimeter, and GS will be given, maybe it's going to be like 2.7 over 2.65. Right? So then you can plug the water content from like 10 to 20%, then you get the dry density. Right? And from that result, you can plot it in this the rho d versus W graph. Here, when the degree of saturation is 100%, and if you put the S as 0.8, then you get the another curve for representing the degree of saturation of 80%, and 60%, you can do the same thing, right? So if you plot it with the standard Proctor test result or the modified Proctor test result, you get this curve. So this is the ZAV curve, and line of optimum is the line that connects the maximum dry density, right? That will be the line of optimum. In general, ZAV and the line of optimum, can you say line of optimum? Almost parallel each other. Then where will be the water content, the optimal water content? Optimal water content is here, right? W opt, and here is another W opt from the modified Proctor test and from the standard Proctor test. I think in the lab you didn't do the modified Proctor test, but still you can get the compaction curve from the standard Proctor test, the lower curve like this, and you can draw the ZAV curve for the degree of saturation 100%, 80%, and 60%. And by comparing this line of optimum to this ZAV curve, you can kind of think that the line of optimum locates between like 70% of degree of saturation to like 80%, right? So this is about 70% to 80%. So that's the optimal condition for the maximum compaction. Question? 질문? 여기서 얘기하는 거니? Here? As you add water, soil gets more compressed, right? And the void ratio, what's the definition of the void ratio? Void volume over solid volume, right? Solid volume will stay the same. What happens to the void volume? 아니, 감소하지. It's gonna decrease. Void volume will decrease because the water is pulling the grains. 에어가 차지하는 비율을 생각할 필요는 없지, 여기서는. 컴팩션은 솔리드만 보면 되는 거거든. 드라이 덴시티만 보면 되는 거거든. 그러니까 캐필러리티가 얘네들이 그레인을 잡아 당기니까 점점 더 이렇게 잘 뭉치게 되는 거잖아. 그러면은 같은 매스인데 전체 볼륨이 줄지. 그죠? 근데 솔리드 볼륨은 그대로지. 왜냐면은 파티클이 어디로 간 건 아니니까. 그러니까 보이드 볼륨이 주는 거죠. 다른 another question? Then, so this was the general result you get from the standard prototest and modified prototest. And we're gonna talk about the structure of the compacted fine grained soil from next page. Okay. So this is about the fine grained soil, and we know that when the water content is larger than the optimum water content, it's called the wet side of optimum. And here is the dry side of optimum. Right? And when you compact the soil at the west side of the optimum, so soil is get more dispersed. This one is dispersed. And here it's flocculated. So when you compact the soil at the dry side of optimum, soil, the fine grained soil tends to be flocculated. And so that's for the A and B and C here. And when you increase the compactive effort, what happens to the clay? So they were like dispersed like this. As you compact more with the higher energy, they get more compressed. So the particle to particle distance will decrease, right? So it gets getting more as you increases the compactive effort, more oriented structure. So in the bottom of the page, dry of optimum, the clay structure independent of the type of compaction, and flocculated face to edge or edge to edge, and randomly oriented. So it will be like more like this, right? And the west side of optimum, if you compact it there, it's face to face fabric. So you get like that. So. And as the compactive effort increases, what happens to dry density? The dry density increases, and void ratio decrease, permeability decrease, and particle structure more parallelly oriented. Question? This one is mixed up. So edge to edge will be like this. So clay particle will have contact with another clay particle at the edge. Face to edge is like this. So face to edge will be like this. 오리엔티드 미닝이 좀 오리엔티드가 뭐니? 오리엔티드 뭐 오리엔티드 약간 한 방향으로 뭔가 경향을 가지는 거? have some tendency? a certain tendency를 가지는 거 아닐까? Parallelly oriented means that they get aligned more parallelly. 이렇게 약간 평행하게 face to face로 이렇게 align 된다는. 그렇죠? edge to edge. edge to edge, face to edge, all together we call it flocculated structure. More oriented structure, it means that as we compact with more higher force, they get more aligned. As we increase the compactive effort, we are pushing it with the higher force, right? So that they get more aligned. Because it's a platy particle, clay has. So we are talking about the fine grained soil, and the soil has clay, and clay minerals are platy, right? 그러니까 platy particle이니까 얘네들이 랜덤하게 이렇게 되어 있을 수도 있지만, because we are compressing it, they get more aligned like this. So you can think of the house of cards. 카드로 만든 집에서, as you increase the load on the house of cards, they get collapse, right? They get collapse and then they align parallelly. 이렇게 되는 거죠. face to face 아니냐고? face to face지. 웨더 오브 옵티멈 아니냐고? 어디 웨더 오브 옵티멈? 아, 여기서 floculated in the dry side of optimum에서 얘기하는 거니? 그걸 곧 얘기해 줄게. 비슷한 게 있어. 그러니까 even though you have a flocculated structure in the initial, as you increase more load, they get parallelly oriented. So you can change the fabric by external force because they can get collapsed. 무너질 수 있으니까 이렇게 스트럭처가. 그죠? Okay. Let's move on. Here, so from now on, we're gonna talk about the engineering properties and the effect of the compaction. So actually, the engineering property of the soil can change depending on whether you compact it in the dry side of the optimum or the wet side of the optimum. And so you can use that characteristic for your structure. Okay? So here, so let's look at the bottom figure first. This is the compaction curve, right? And this is the normal compaction curve. Here is the maximum dry density. And here, let me use the red one. Optimum water content, right? And if you plot it, you could extend the line like this. The right side of this red line is the west side. And here is dry side, right? The left side is the dry side. And this is the experimental result that the people have presented before. And permeability decreases as you compact with the higher water content. So as the water content increases, the permeability decreases, right? And the K decreases. And when you compact it with the west side of optimum, it doesn't very much affected by, it's not very much affected by the water content change. So K is more consistent with increasing water content. So K is here the permeability. Okay? Permeability here is more consistent if you compact it west side of optimum. So, but when you compact it dry side optimum, as the water content increases, the permeability decreases abruptly, right? And very significantly. And it says the same thing at the bottom. Then, here's the question. So when you build a earth dam to make a reservoir, which side is more preferred for the compaction? So in the dam core, I think I showed you before, in the dam core you have a clay core, right? Core is made of clay to be impermeable, and that clay needs to be compacted when you build it, right? And which side is more preferred? West side is more preferred, right? Because when you compact it in the dry side, after the completion, when you flow the water, and water will increase the water content, then that will change the permeability. Right? So you don't want to have the change. You want the soil have a constant permeability, right, over time or over the range of water content. Okay. On the next page, compressibility. So dry compacted soil has like this kind of a flocculated structure, right? Let me draw this one. So now you have a clay soil and you're increasing the load. And when the stress is small, they get just compressed a little bit elastically like this, so that here the fabric is preserved. And then you have a less change in void ratio. So this is the void ratio. And for the same amount of the soil, when you have so now you have like dispersed fabric. The same amount of the stress, right? Delta sigma to sigma is here the stress. Here you have a more compressible. But this flocculate structure, you can see that it's not very stable. Right? They can collapse with the higher, if you increase the stress, increase the load. So if this sigma increases and this high enough to change the fabric, then they get collapsed and they becomes like more like dispersed and the face-to-face aggregation. So that's what it shows at the bottom. At high stresses, here, even though you have the dry compacted soil, starting with the flocculate structure, but at some point, as it reaches some threshold stress, you get the aggregate structure. So here the fabric change. Of course. And this is a wet compacted soil. So in the blank at the last sentences, the sample compacted on the west side is more compressible or less compressible in low stresses? 마지막 문장의 blank, what would be the proper word? Less or more? More. But it can be less compressible in high stress than the one compacted on the dry side, right? Can we move on? Okay. More and less. Aggregated structure. aggregated. Aggregated structure. Rebound for both sample means so you starting from here, you increasing the load. So as you compress the soil, you get to this point. So void ratio has changes by this much, right? And rebound means that you are lifting the dead weight. So you're decreasing the load. So now it doesn't go all the way to the original state, it will stay somewhere here. It will end up somewhere here. So that's a rebound. Rebound means that the unloading. 다른 거? Another question? 그래. I'll scan it and also the note will be posted on the website. Okay? 올려줄게. 혹시나 못 쓴 사람들을 위해서. So let's move on. Swelling. What is swelling? Swelling is when you add the water, their volume expand. So volume increases. It's called the swelling. Okay? So here, if you compact the soil if you compact at the dry side of optimum, the water content can increase if it rains, right? So then you get the higher swelling potential. And when you compact it at the dry side, the wet side, you have more water, and when it dries, it may shrink, right? So you have a higher shrinkage potential. So at the bottom here, clay compacted on the answer is dry. Dry side of optimum, the larger deficiency of water and therefore have a larger tendency to absorb water and swell more. Actually, it's too obvious, very straightforward. Almost there. So then let's move on to the strength. Here, this is very good result. And where is the compaction curve? Compaction curve is here. The C, the bottom right figure is the compaction curve. You have a water content versus the dry unit weight. And they have done their 6 experiment, and you have a 6 points, the data points. 1, 2 is sample 1 and sample number 2 is compacted dry side, right? Dry compacted soil. And 3 is optimally compacted, right? It's optimum. And 4, 5, 6 is wet compacted. Right? And from there, so let's keep in mind that the number 1 and number 2 is dry compacted. Let's compare to the degree of particle orientation here. In the figure left, randomly oriented, as the degree of particle orientation goes to 0, it's more like randomly oriented, like this. And as the number increases, it's like parallelly oriented, right? So you can see that the number 1 and number 2 is a dry side compacted soil, and it has more randomly oriented structure. And if it's compacted in the right side or the west side of the optimum, you have more parallelly oriented. Huh? Wait. Sorry. This is random. So it's just the same and consistent that we have learned just before. Right? And eventually our purpose is to compare it with the shear strength, the strength of the soil. Here, the top figure shows the strength. 4, 5, 6. Where is the 4, 5, 6? 4, 5, 6 is what? West side compacted soil, right? And the 1, 2, 3. 3 is the maximum, this is the optimum, and 1 and 2 is the dry side of compacted soil. And what's the difference? West side, it's more like very strain hardening behavior. It's like ductile behavior, right? And the dry side, the number 1 and number 2, it shows brittle behavior, right? So what does it remind you? Plastic, and this one is brittle. Behavior. And we are talking about fine grained soil, right? What does it remain? Does it remind you of the plasticity, plastic limit and the liquid limit and the liquidity index? Huh? Right. I think if you remember this one, you have a water content when the PL and L is here, and before here you have a brittle behavior, you have plastic behavior, this is the liquid, right? And what about the liquidity index? What's the definition of the liquidity index? PL 빼기 LL? 분자부터 기억나니? 분모? PI. 분자? water content, natural water content minus plastic limit이지. 맞지? natural water content minus plastic limit. So when the liquidity index is less than 0, it typically shows the brittle behavior, right? So this is the dry condition, dry compacted soil. And if the liquidity index is between 0 and 1, shows plastic behavior. And this one correlates to this soil, and this soil correlates to this wet soil, wet compacted soil. And if you compare the strengths between dry and wet, which one is bigger? 민성. 누구한테 물어봤을까? 민성이한테 물어봤네? 상윤. Which one is bigger? Dry compacted soil. So this is actually they done these experiment with the same soil. 똑같은 soil 가지고 실험 여러 번 한 거야. They repeated their strength test several times with the same soil. And which one is bigger? Dry compacted soil or wet compacted soil? Which one have the higher strength? Wet? Why? Huh? Dry? Why? No, you can actually, the graph says the result. It's telling you the result. The first graph. So this graph shows telling you that the sample number 1 can resist this amount of stress, 500. And number 2 can resist about like 450. And what about the wet soil here? Probably this is the maximum, right? Number 4 is about 200 kilonewton per square meter. So that's about 200 kilopascal, right? Number 5, where's number 5? Maybe this one is number 5. Number 5 is about 150. Number 6 is about 100. Huh? So it means that this maximum value is the strength of the soil, okay, of this curve. Right? So dry compacted soil has the strength of about like 400 to 500 kilopascal, while the wet side compacted soil has the strength of like 100 to 200 kilopascal. Right? So obviously, dry side soil has the higher strength. Does it make sense? Okay. So that's how you read the stress-strain curve. I think you and I are familiar with the stress-strain curve. Huh? 그렇죠? So the last question here, which side of the optimum makes the compacted kaolinite specimen more rigid and stronger? 물어봐야겠다. 창규. Dry side, huh? Or dry compacted soil, huh? In summary, so this is the summary table. I think we can just go very quickly. We are running out of time. So dry side, if you compact the dry side, the structure will be more like flocculated or randomly oriented. Can you see well? Randomly oriented. Okay, this might be better. And here, if you compact the wet side, dispersed or aggregated and more parallelly oriented. Okay, 됐다. And the permeability, when you compact the dry side, it's more permeable. So if you remember this kind of curve, right? W and K, right? So the left side is wet side compacted soil, right? And the right side is less permeable. Okay? And when we talk about the compressibility, this is the dry side compacted soil is more compressible at a high stress level, and here more compressible at low stress level. And swelling potential, dry side has the high swelling potential. And here you have high shrinkage potential. Bad writing. in terms of the strength, dry compacted soil has greater strength, and wet compacted soil has lower strength. And the behavior characteristic is the brittle behavior. And wet side compacted soil shows the plastic behavior. And applications. So when we compact the soil with a little bit less than the optimum water content, then it has more strength, right? So application is dry compacted soil is useful when you want to increase the strength and the stiffness. So for example, it's good for highway, subgrade, or the shell over earth stem. And west side compacted soil, it has low strength. So strength-wise, it's not good, but has very less permeability. Right? So it is good for controlling the permeability. So the good application will be the earth stem core. Almost there. Okay, can we move on? 거의 된 것 같은데. Okay, so next page, if you go move on to the next page, page 7, it's about compaction of granular soils, right? And 이따가 보여줄게. So now we're talking about the granular soil. It's a coarse-grained soil. You can have loosely compacted soil or loose packing, and densely compacted soil, dense packing, and honeycomb fabric. So this is very natural fabric that you can find in nature only. You cannot make this kind of honeycomb fabric in lab or artificially. But this is metastable structure, so it looks like very unstable, right? If there's an earthquake, it's gonna crush it very easily, right? So it's a loose fabric, and it's not good for liquefaction, and it can cause the sand boil. For the coarse grain soil, most efficient method is vibration for the compaction, and no electric forces due to small specific surface area, and gravity forces between particles are greater than surface forces. Soils easily move from a looser state into a denser packing through vibration. So when you compact like this kind of a sandy soil, easiest way is to just shake it, okay? And apply the, so there's a roller with some vibrator. So it has some frequency, and when you go over the pavement, they give the vibration to the soil together. Okay? That's for specifically designed for the coarse grain soil. And maximum void ratio is the loosest possible state for a dry soil. And the minimum void ratio is the densest possible state achieved by mechanical means, but without grain crushing. In general, maximum void ratio, we pour the soil on a beaker with a funnel, and then you get the loosest state. You don't apply any vibration or the compactive effort. And densest state, you can get it from the compaction test. So E mean and the E maximum, you get it from the experiment. And if you know the void ratio of the given soil, then you can get the relative density. Relative density is a very useful term to find out how well the soil is compacted. So relative density is used to characterize the denseness of the natural granular soil. And the definition is this one. E max minus E mean, and the E max minus E over E max minus E mean. So here the E is the void ratio of a given soil. Oh, here is already. So what happens if the void ratio of the soil is same with the E maximum? What's the relative density? 0%, right? 0%. And if the void ratio is the same with this minimum void ratio, and relative density is 100%, right? So relative density increases, it means that the soil is more compacted. So when you look at the table here, very loose soil, the relative density is, ranges from 0 to 15%. And if the relative density ranges from 15 to 35%, it's a loose state. And 35 to 65%, that's a medium dense state. And 65 to 85% is a dense state. And when it's 80 to 100%, it's very dense state. Okay? So this table is a very useful table to describe the soil. Okay? And in terms of dry density, actually you can convert this relative density equation in terms of the dry density. Rho d is rho s over 1 plus E. So rho d is inversely proportional to the void ratio. So chup chup chup. This is max. Min. Sorry, this is the minimum. Minus max. %. And you have another term, it's called the density index. Density index is rho d minus rho d mean over rho d max or minus rho d mean. But this density index is different from the relative density. It's not the same. 질문 있니? 맞아? 질문? 아닌 것 같아. Just give me 3 minutes more, then we're done. Okay, so move on. The next page shows the importance of pore size. Here, the top figure and the bottom figure, which one have the higher void ratio? No, actually it's the same. So then, dry density will be the same, right? Void ratio is, because the void ratio is the same. But you can see that which one will be more stronger? The top one will have more stabilized structure, right? So when you compress it, it's gonna compress less, but this one will give you more compression, right? Or the more settlement. So people say that relative density or void ratio alone is not sufficient to characterize the engineering properties of granular soil. Okay? So it highlights that the relative density is important, but it's not the all information that it can tell you, right? And two soil with the same relative density or the void ratio may contain very different pore size. That is, the pore size distribution probably is the better parameter to correlate with the engineering properties. So this figure highlights that also the pore size is very important for the engineering property. I think this one, the bottom, the two paragraph, you can read it for your assignment.